iPad, right? Or let's try.
Well, yeah, let's try with your iPad.
ข้างบนนี้ใครนั่งอยู่นะครับในห้องเจมส์อะครับอ๋อนีโอครับเขาใช้ iPad นะครับไม่รู้มันเรคคอร์ดได้ป่ะครับเดี๋ยวลองดูแล้วกันนะครับ This one. Okay. It's strange that it's freaking. Let me go back to the normal first. I don't know what. Oh. Maybe I stop correctly before. Okay, it's working, but sorry for the dead dot there.
Okay, it's fine. We'll figure out how to do that.
Okay. I think it's extend desktop maybe.
Okay, now I just can do that.
Okay.
Yeah, that
So-
was a good move.
Okay. We will use Paramate notebook first, and then we
Yes,
switch.
yes,
by-
and then we switch.
Okay.
And I'll return the kit.
เอาลองอีกทีเหรอลองอีกรอบเหรอครับอ๋อ try once more okay because they wanna test that we can record แล้วนะ Time to switch.อ๋อแล้วต้องใช้นู้นแทนเลยอ๋อ
If you want, I can send you the
อ๋อ
PowerPoint.
you can send
Yeah,
มี
I
PowerPoint
think we can do that.
yeah we can
Let me try that.
because we want to record the screen as well the block links you can download Oh, we have two MacBooks. PDF ก็ได้by email Actually, you can use your own, but I think we want to record it.
Well, I'll send you. No, let's make sure it's not a large file. So I'm okay. You can just move to the slide and put it there. Yeah, so there, sorry to send you. I sent it.
It's all in the here.
Okay,
Not,
yeah,
not
yeah.
in,
I
not
can
in
send
the,
also the.
in the not link. Oh,
Okay,
delay,
there, it is just
delay.
when to see it. You just need to download. No, no need to want it. And then download. There's the download somewhere. Yeah, download that. You can go through the slides so that you. Yeah, I don't use special effects. Just this. Okay, then that should work. It's just perfect. Thank you. So then I will be using someone else's laptop.
This one.
This one, okay. Then is there a thing to
Because or I will try my own. I'm not sure that they need not on
the laptop? Compare with that. I'm okay with that. Because here it's probably for
the line.
when it's time.
So let's get started. Let's do this more, like in the relaxed style, informal ways. Even we do this kind of small symposium or small conference here. I just realized that we have no external visitors. Thank you for coming here. And the plan is that after the conference, probably we can show you guys around of Vistec. Okay. So the idea of today, we call this is like the seminar series. Is we want to discuss more on the physical AI and robotics. Why physical AI and robotics is important? I think nowadays. So, I think this is the time of AI. Everyone knows artificial intelligence, machine learning, and robotics. So basically, they try to mix things together, right? Today we have 4 talks. First, I will give you a short introduction of our schools and also a bit of our research. So I try to keep the time as short as possible, but at the same time, I will just go a little bit of some mechanism that we developed. Maybe it might be interesting for you guys to learn, and then we can discuss afterwards. After my talk, there will be our honor professors, Professor Dominicos from NTU. So he will present on human-robot interactions. Okay? And then afterwards, we will have 2 more talks related to assistive technologies from Dr. Shai Chan and Mr. Thanapon. Okay, so the last talk, I invite one of our PhD student, Mr. Thanapon, to give his recent work to present to everyone because he came up with the very interesting technique to adapt the parameters. When you have machine learning, you need to set up parameters, okay, manually, empirically. He came up with a technique that you can adjust those parameters in real time. Okay, so he will talk about that. So, and that's why we want to, first talk a little bit about robotics and machine learning, human-machine interactions, assistive technologies, and how we can fine-tune the machine learning parameters. So, okay. Can I share my slide? It's not working? Doesn't work. Okay, maybe. Okay, maybe it should work now. Okay, maybe let's try again. Okay, so it should work now. So by the way, today and especially in our research team, we are focused on the physical AI, not just having the brain or computer software on the machine and let the machine learn something, but we are mainly emphasize on embodied aspects. What does it mean, embodiment? Embodiment means that the robot or the physical system should be able to exploit their physics, either to offload computational aspect of the brain or for interaction to get more and more data for learning and adaptation. And that's why we are focusing here on the physically embodied AI. Okay, I put the embodied aspect here because I want to emphasize that AI requires brain, body, and of course, interactions. I can walk, I can run, I can jump because my body interacts with the gravity, with the floor on the ground. Okay? That's the key aspect here. Looking at this animal, so when you look at this animal, the newborn cattle, it can quickly learn how to walk within minutes. Okay? This is very amazing how nature learns how to do something at birth. But if you look at nowadays machine learning technique, reinforcement learning, it takes a lot of computational powers. You need to learn with the multiple robots in simulations, multiple hours or even days or weeks to get a good behaviors for that. Okay? But animal doesn't do so. That is still a big gap between machine and natures. Okay? And therefore, in our research lab, we try to close this gap, or we try to make this gap become small and smaller. We look at the different aspects of artificial intelligence. So basically, we try to turn from the digital AI into the physical embodied AI here. And at our school, at IST, we want to develop AI to achieve different functions. For example, we are talking about autonomy. Let's say you have robot, it should be able to move autonomously or less human interventions. It should be able to do generalization. Generalization is also a very important feature for machine learning. So you should be able to learn something and take the learned knowledge to apply to unlearned thing. That's about the generalizations. You should be able to scale from small tasks to larger tasks or small group to larger group. Security, resilience, and interaction with the world. All these are the important functions that we find ourselves that we should develop AI that can do all this. Therefore, at our research or our school at IST, Information Science Technologies, we work on 3 aspects of artificial intelligence. First, we look at the physical intelligence, meaning the physical body. We are working on how we can build the robot body such that the system or the robot can exploit its own existing body for efficient locomotion, learning, and adaptations. Second one is about computational aspect on the computational intelligence. That is like standard machine learning technique that people use as the model. Last one, we look at the infrastructure of AI, which means that if you want to train the model, you need to train the model in the clusters. What happens if you training the model in the big cluster and some of the GPU in the cluster drop out? Or the cluster has some, fall? How we can readapt the configuration of the cluster such that the system doesn't affect while learning on that. So that is about the infrastructure intelligence of AI. So all this, we go further into 7 wonders of AI now. This means that we look at the AI as acting, which means that a robot that should be able to perform behaviors. We should have AI that can sensing, AI that has body for sensing and acting, AI that can think, or AI modeling, and also the last 2 things is about the AI data centers and AI system. Okay? These are all aspects that we are working on with a number of professors here. Application include medical inspections, legal assistance, and climate change prediction, for example. These are some list of applications that we have, or we are applying our technique to those domains. So if you look at the AI as such, people think in the past AI as the modeling aspect, like the software parts, but we expand this model into the big pictures, including the AI modeling, AI system, AI body. Body basically covers the system and modeling because the body is a part that allows AI to interact, to move, to perceive informations. And we have AI sensing and acting, all this. So these are all faculty members, including me. We have 5 faculty members and 1 more adjunct professors. He is actually originally also from NTU. So he joined us as an adjunct for working on quantum computing parts. So me and my team, we are working on AI acting, physical interaction with the environment like robotics and AI. Second professor, he's working on AI sensing and interpretations. The third one, he's working on the modeling large language model. The fourth one, he's working on the visual information processing, analysis, and data synthesis. The last one is he's working on the data network and also the infrastructure of AI. Okay? These are all professors or the faculty members who work towards that vision or directions that I just present. So now I want to go further in terms of our research domain. So I have until 2, so I will try my best to finish everything at 2. I will introduce some of our research in domain of robotic and AI further. So basically, we turn the digital AI into the physically interactive AI, okay? AI that can move, that can interact, that's require body. This is one of the big picture or the diagram that whenever we talk about physically embodied AI, I try to draw this diagram. This diagram consists of 3 entities: the brain, which is the software part, the body, which is the physical part, and the last one is, of course, the environment that the body can interact with the environment by performing behaviors, perceiving informations, like the arrow up and down, okay? And inside the body, you can also send your informations, like my movement and so on and so forth. So this is the big picture that integrate everything into the physically embodied AI, okay? One more thing which is interesting here is this loop here. This is the loop that the environment feeds something back to the body, and the body directly interact to the environment. That's what we mean by prefix or passive adaptations. Imagine that if you have the robot with the soft body, soft material, you can let the robot adapt the body itself to the softness to deal with obstacle without controlling it. That's what we mean by that lowest loop. By having these architectures, we can offload complex computational powers into the body. Body can take care of something as the minor perturbations. If the perturbation becomes strong, the brain kick in. That's the idea, okay? So now, to go into more detail here, what we are doing here is that we try to look into natures. For me, I love natures because I think nature is a good blueprint. We can learn many things from natures, from different levels. This diagram, basically the detail that we do research in terms of the biomechanics, which is the body, how you can build the body of robot in the sensible way or make useful way. This way, we look at the structure of animals. Upper the biomechanics, we have the locomotion control and the higher level control. Okay? So animal, or even for us, we don't always think how to walk. We just initiate our locomotion, and the rest will work on the spinal cord level. So that's the locomotion level. The brain make a decision to initiate our motion to make a left or right turn. That's how it works. So we try to translate from the right side, which we learn from nature, to the left side, which we implement on the artificial system here. Okay, by doing this, by learning from nature, we hope that we can speed up first the learning process. Okay? We can speed up the learning process for machine learning aspect. I will show you some example how we can speed up the learning from many days, many hours to minutes. We can learn everything in a few minutes and even learn in a few seconds. Okay, I'm gonna show that. So this is the animation showing traditional way of doing. I want to say that this is the one I show here is not the only way, but it's an option that you can use the technique to make the robot learn how to do things. But this animation show the traditional way, like model-based control. You need to derive mathematical model, or you can use data-driven approach. You let the system learn from the data The system interact with the environment to gather the data and learn, try to figure out what is the best policy or the best behaviors that it should perform. So by having this traditional aspect, one is you need a lot of engineering knowledge to build up the mathematical equation, or the other one is it takes longer time for learning, many days, many hours. So then if we look at the why the machine learning nowadays is good, but there's still a big gap. So first is computational inefficiency. It requires GPU. The brain doesn't have such large capacity to calculate as GPU, but the brain works in the different manners. Time consuming, it requires rich information because you don't know what information I need to move my robot. The best way is you just feed everything you have, many kind of sensors that you have for the robot into the model, and let's hope that the model can find out what is the best mapping between sensor and motor actions. The last thing is probably you might end up with a black box, which you don't understand what's going on inside. To address all these points, we came up with a technique. First we start from natures. We look at what is the key ingredient in the animal behaviors. So we found that animal doesn't have a big network, but it has sub-network. Different network has its own function. For example, we break down the complex network into sub-network module, and because of this, we create the first simple network, which consists of 2 neurons. By having these two neurons fully connected, it creates rhythmic pattern. Having this rhythmic pattern is the baseline pattern that can generate movement, rhythmic motions. Afterwards, what you need next is that you need to shape that patterns into the proper behaviors or proper motor patterns. You translate from the original rhythmic pattern from 2 neurons in the blue through the red neurons here. This is just nonlinear mapping from one rhythmic pattern into more complex. What we do here is that basically once you have these architectures, you just learn the connection from the blue or from the red to the yellow neurons here. And that's make the network or the parameter become small. You don't need to learn the big network because you create this from your understandings. By having this technique, you can use any kind of machine learning to adapt these synaptic connections from the red neurons to the output neurons. This way, we can speed up the learning process. The robot can learn here within a few minutes, like let's say here 20 minutes. Okay, we can scale down from hours to minutes. Now you get the idea now. So the take-home message here is that instead of starting from scratch, we should start from something that understandable and we know the functions. What do we need? Okay? Now I skip all this to go to the next one. So we managed to set up the predefined network. This network is important because I think afterwards my postdoc, Dr. Chai Chan, he will talk about his exoskeletons, where we also use the same network architectures for different machines. It works because let this hexapod robot walk or quadruped robot walk or even 2-leg robot. You need the minimal setup which require rhythmic pattern. When I walk, I swing my leg forward and backward. That's rhythmic pattern. Then the second layers of the network just shape the rhythmic pattern into other pattern that require for that specific machine. That's how it works here. The next one I want to show here is that can we increase or increase the efficiency but decrease the learning and adaptation time from minutes to seconds. Okay? The key message, I skip all this, but one of the key message I want to emphasize here is that this is what we call predictive encoding. So what do we do here? Imagine when you move, you walk, you also expect something in return. When I swing my leg and touch to the ground, according to these motor actions, I expect that I'm gonna get the force feedback at the end of my actions. This is predictions, okay? According to this concept, whatever you do, walking, manipulating something, you perform action, you expect something in return. That's what we call expectations, okay? Expected sensory feedback. What you're gonna do here is that we take the motor patterns that we drive the locomotions, and we translate this motor pattern here through what we call forward model. Forward model is the neuron model that translates the motor patterns that you drive the behaviors into expected pattern from sensor feedback. Okay? In this case, we translate the original rhythmic pattern here into expected foot contact feedback by using a neural network. So basically, it's nothing, it's just nonlinear mapping from this into expected sensor feedback. Now, what you do next is that you compare this expectation with the real feedback. Okay? If the expect and the real feedback, they do match, then you don't have prediction errors. Then everything happy. The system doesn't have to do anything. It behaves as it is. But if the expectations and the feedback, they don't match, when you compare, you get the error here. Okay? It's just comparing actual with your reference in your mind. We call this is prediction errors. And this is a very good information because you can use these error informations by using error-based learning. Okay? This is one of the error-based learning we use here. We take the error here through these equations. By having this minimization of the errors, we take this further, to let this learning mechanism minimize the error by adjusting some neuron parameters here. Okay? By having this closed loop, you can minimize the errors by adapting the neuron parameter according to your control model. This way, what we do here is that in this work, first we let the robot perform some arbitrary behaviors. What the robot needs to learn is that it needs to learn to synchronize the legs such that it doesn't have high error. What does it mean? Imagine I am the four-legged robot. At the beginning, all of my legs and my arms stay on the ground. When I oscillate when I try to lift off one of my leg or my arm, my motor command say I need to lift, but expectation means if I can lift, the ground contact should be 0. But if I cannot lift because it's non-synchronizations, the ground contact is become non-zero. It become some values. Okay? This means that I get the prediction errors here. I take these errors, adjust the phase relations between legs. Okay? By having this simple trick, you can little by little readjust the parameters such that the system from the beginning, look at here, this means the leg cannot really lift. Why the expected say this is the period I should touch the ground, I should off the ground, and this is the real feedback. I cannot really lift and place my foot properly. Most of the time it stay on the ground. After some time, in this case it takes like 10 seconds. This is the parameter that we learn. Okay? I will not go into detail, but depend on your model. You little by little adjust your parameter from zeros to some values. You see the progression of this. At some point here, you have these oscillations that follow these expectations. Then the learning will more or less stop. This way, we implement this technique into legged robots. The robots start to oscillate. So while oscillating this, at the beginning, the foot cannot really lift. And because of the mismatch error predictions, we use that information to readjust the phase relation between the center pattern generator or between oscillators. Little by little, the leg starts to find out what would be the good phase shift by itself. And after 20 seconds, the system learns how to walk. This is the decentralized manners. We don't let the controller on each leg talk to each other directly, but through the sensor feedback. Okay? So interestingly, the behavior converge to locomotions that compatible to the stick insects. What do we learn from this research? First, we can use just only foot contact information, which is enough for forming locomotion here. We don't use any joint angle, just only the global foot contact information that enough to form a behavior, a stable behavior, which comparable to stick insects. I will skip all this. This is about the learning and memories. I will skip all this. So this is the other research. We look at how you can store informations into the machines, like robots. This is the example that demonstrates, if you look at the cats, the cat can walk, it has the visual information. Interestingly, the hind leg can step over the obstacle without seeing it. This is because the cat can store the motor pattern of the front legs into the brain, and it releases that information later. That is a kind of working memories. We do the same thing here for robots. You can see the middle leg and the hind leg will not touch the obstacle because we store the touching of obstacle from the front leg into the brain of the robot, such that that working memory can store this information and try to match to the walking speed and release the action afterwards in time. Okay? So, yes. One last thing I just want to shortly show here is about the dung beetle. Here, one of my favorite work. We learned from the dung beetle, it can transport a huge object. And I try the same thing myself here, but it's difficult. Okay? I found a big ball and then I try to push, but it doesn't work. And that's why we try to learn how the dung beetle managed to do this. Okay? So from this, we came up with, like different subtasks. We look at the biomechanics here, and that's why I focus on also the embodiment. We look at how we can create the dung beetle-like robot from learning from natures. We look at the structure of the dung beetle, building the robot out of that, and we learn some rules from the dung beetle by visual observation here. And we came up with a neural network that can make the robot roll the ball like the dung beetle. Okay? Before achieving this, we implement a simple mechanisms. I will skip all this. One last slide of mine. Okay. We look at the most simple way of controlling behavior. This is what we call walknet. Walknet is just reflex-based control. What does it mean? It means that you can use only sensor feedback to define or switch states of your movement. For example, we have the walknet, this is the walknet that introduced by very famous biologist Hook Cruisers. We take the walknet and we adapt the walknet mechanisms, which is based on only the sensor feedback, into what we call rownet. And we introduced this walknet and rownet on the dung beetle. This is our first version of dung beetle-like robot. Basically, this robot, it doesn't have internal oscillators. It just relies on the states switching from joint angle and foot contact. Let's say what it does is that if the foot comes to the front to the certain threshold, it places the leg down. If the leg touch the ground, it switches the leg to backwards. By having these simple rules, just 3 rules, we can form a behaviors. Or in this case, 2 behaviors, walking and rolling the ball. So what I want to summarize here is basically what I show here is that first take-home message is that if you want to reduce the computational powers, you can try to set up the network architectures that require what you need. The second thing is that once you can reduce that complexities, you can just learn only a few parameters. The second thing is that you need to try to find a good error functions. In this case, it's the prediction errors to adapt your control parameters. So we have also other works on different robots, including exoskeletons, and I think this will be my last slide. So in total, in our research, we work on 7 things of robotics as well. We start from bio-inspired robotics, look at how animal or nature works. We start to move into non-conventional robots, like soft robots. We look at industrial robotics here, also in terms of drones. We look at the drones because drone is a platform that can have very dynamic behaviors. We are interested in how can deal with the complex dynamic behaviors because walking, you can have a certain dynamics, but drone flying, it has more highly dynamic behavior. And that's why we want to see how we can come up with the neural mechanism that can adapt to the high dynamic. We work also on the bio-inspired creepers. Medical application with Dr. Chai Chan will talk about that. Inspection robotics and service robotics. Sorry, I think that's all of our research. So basically, to sum up, we try to bring from the right side to the left side by understanding natures, and hopefully we get new technologies. Second thing, we can come up with more understanding of how nature works. I think that's all from my side. I think with this, I would like to thank for your attention. Okay. So if you have immediate questions, you can ask. Otherwise, make note of your questions, and then we will discuss everything at the end of the talks. So then I think so you have the slide here, right? Okay. So I think let me introduce our next speakers, Professor Domenico Campolo. He's the full professor from NTU, Nanyang Institute of Technologies. He's also at the same time the director of the Research Center for Rehabilitations. It's our honor and it's also my pleasure to have him here and also spend some time with us here. So without ado, then let me give the floor to Professor Domenico. Thank you.
Thank you very much, Paramit. Thanks for the invitation, for the very generous hospitality. I met many students, many researchers. It's really a pleasure. I see that, like Singapore student, you like to sit at the back, but it's okay. I need to familiarize with this. Let's see, yes, okay. I need to learn to use this, but it's fine. All right, my name is Domenico, and I'm, well, from Singapore, not originally. I'm with NTU, and I work in robotics. I will introduce myself in terms of research very soon, but let me say that since a few months, I'm also affiliated with the Rehabilitation Research Institute of Singapore, where we do things that I see as many common areas of possible collaboration. So I'll be happy to discuss that later. So, the title. The title is basically Biological Motor Principles. It's a very general presentation. I know there are persons from last October in FIBO. It will be different. This is to give you an idea of certain topics that I'm interested in, and I'm very happy to discuss anytime later tomorrow. So that's the meaning of this presentation, the purpose of this presentation. Okay, this is a bit what I've been doing graphically since, I would say, 20 years now. I'm Italian, so I used to, after postdoc, I used to work in Rome. I was in a bioengineering department inside a medical school. For me, that was a very formative time because really I started to talk to clinicians and doctors every day. And that changed a bit the way I think. So I think it's important to have clinicians nearby for certain topics. I moved to NTU in 2009, and I've been working in robotics. As you see, this slide is full of things, but there are actually more people than robots. I'm actually more interested in people than robots. So one idea is to learn a bit how we do things. You mentioned many important things from embodied intelligence and so on. And maybe use this one to teach our robots, and maybe use the robots as a test bed. I guess you do this every day in here. You have biological theories, and you use your robots to test if a theory really holds in the real life. Because you cannot always simulate everything, so the robot is a physical simulator if you want. However, sometimes robots can also become useful for humans because sometimes we lose abilities. So one of the applications of my work is rehab or assistive robotics. And the name there, RTCares, is a startup company that, together with a postdoc of mine, we kicked off in 2017. And the robot is one robot that we've been working for many years and then became a product. Today I will not talk about this. I mentioned last time, but if you're interested, we can discuss. Today, I will talk more about this kind of experiment. In fact, a subtitle for this talk could be, "It's all in the wrist." In Italian, in English, I'm not sure in Thai, there's a saying, "It's all in the wrist," meaning that somehow the skill is in the wrist. And let me take you through an excursion of the work I've been doing here. So, that's the alternative title. There's a little bit of history. I think it's nice to start with some history. And then I will go to more recent and more maybe technical parts. I don't expect to cover everything. This is a general talk. If you have interest in these topics, we can discuss later on the technical aspects. But if you don't follow certain aspects, don't worry. It's not meant to be detailed here. All right, a bit of history. So there is this nice paper that I really recommend you read. Neville Hogan is a big name in this field, about theoretical neuroscience, motor neuroscience. As you know, physics went from observations, so you had centuries, if not millennia, of people looking at the star, taking notes of what happens, and filling up records and records of events. Like eclipse or other sort of astronomical events. But then it came a time where someone, Kepler for example, went from heuristics to curve fitting. He came up with a set of 3 simple rules that actually would describe all the movements that was observable in the sky. Basically, he managed to put together tons and tons of papers in just 3 laws. And that's is a bit what counts as curve fitting in this environment. And later on, actually, you have other people who were able actually to synthesize this knowledge with only 3 letters, F, M, and A, in a single equation. And that equation would apply to stones, apples, moons, and so on. And that is amazing. And there are 2 versions of this. The first one that everybody knows, and maybe the second one, which we might not use every day, but it's an equivalent form. But that one is even a bit more useful in certain contexts. So the same thing might happen for neuroscience. That was for physics, for astronomy, right? But for neuroscience, probably we are heading there. But we had many decades of observations. Then there is someone who came up with laws that try to describe. This is what I mean by biological laws. I will explain in a second. And maybe it's time to move to some more theoretical framework that helps understanding what's going on. What do I mean by this? So people have observed humans for a long time, but only maybe in the last 100 years or slightly more, you were able to record quantitatively what happens. In the 70s, in the 80s, you started to see the first robots. And these allowed studies which were more objective. These are upper limb movements. I work a lot on the upper limb, so I do not walk. My research is not about locomotion. So it's slightly different from the things you see, but probably there is some connection even there. And people have observed human motion in several conditions. These are reaching tasks. You go from A to B, B to C, and so on. And they have questions whether, well, does the human brain organize its movements in terms of endpoints or joint spaces? In your lab, you work a lot on actuators that are at each joint. Actually, by the way, this could be one leg of your insect, right? You have 3 motors. You can think of 2 or 3 motors also for an arm like that. So is the brain thinking in terms of X and Y at the hand, or maybe theta 1, theta 2, theta 3 angles at the joints? Well, it's clear that, I'm not sure you can read from there, but there are 2 plots. These are speeds at the hand level and speeds at the joint level, so joint velocity and hand speed. And independently of the movements, the hand velocities are actually quite similar, but the joint velocities are very different. So maybe, at least for these tasks, which are reaching, remember, they are very different from your locomotion. This changes with the task, but for these tasks, it's planar reaching, so you reach on a plane. The brain is really organizing movements from the hand perspective. And this one has been then synthesized with laws that are, for example, minimum or maximum smoothness. This goes by the name of minimum jerk. Jerk is the derivative of acceleration. So if you want a smooth movement, you try to minimize what is known as jerk, or third derivative of the acceleration, or maybe you minimize the rate of change of torques. There are many hypotheses, and these equations, which are captured here, actually are able to some extent to describe these motions. From time to time, I put books that I like very much, like these human robotics books by a colleague. It's a very interesting reading. And one thing that I'm very interested, because I work on upper limb, upper limb for humans, even with the most simplistic model, has 7 degrees of freedom. And if you have a degree of freedom for a rigid object, this thing I'm holding is 6, right? In space, you need 3 orientations, 3 degrees for orientation, 3 degrees for translation. But my arm has at least 7 degrees of freedom. You can count from shoulder to elbow to wrist. So this is called redundancy. This is typical. The human body, I guess also the insects' bodies, they have way more degrees of freedom, kinematic degrees of freedom, even more muscular degrees of freedom, but let's stay on the kinematics, than necessary for most tasks. That means that the brain has to come up with a solution. So I could, if I need to press the level at the elevator, I can do this in multiple ways, and the brain has to decide one of these ways. And we do this without thinking much. But for robots, it's a big headache. Let's see how humans do it. So in the 60s here, Bernstein, a Soviet researcher, actually started to look at very highly skilled motions. He's a blacksmith. So these are very skilled motions. If I try to do this task, I would probably injure myself. And he started to look at how all the joints would move. This is the beginning of your OptiTrack, but he had light bulbs. So that was the very beginning of photogrammetry, right? And by looking at these motions, he actually started to hypothesize some behaviors. So there are some ideas, but current theories that work for the plane start to fail when you go in 3D, when you start to do things in the vertical dimensions or even in rotations. They fail because the human arm is devoted to multiple tasks. So my arm is used to feed myself, let's say to comb. I don't comb very often, but to comb myself, to pick objects, to call the elevator, to signal okay to my friends, and so on. So there are many tasks. But perhaps a leg is less multitasked. So there is one element in the human body that is devoted to basically one and only one task, and that's the human eyes. So many years ago, I started reading about eye movements. The reason is that I was and I'm still very interested in 3D rotations, and the human eye is a ball in a socket, if you want to have a simplistic model, mechanical model, and is devoted to only one task, gazing. That's what the eye does. You might guess how many degrees of freedom in the actual eye. Well, the actual eye has 3 degrees of freedom. There are 3 pairs of muscles, and they are devoted to actuating these degrees of freedom. Now, the interesting thing is that voluntarily, I can only move in 2D. But my brain, our brain, is able to even move the torsion, and that's something that's been studied for a long time. So in 1847, there was no electricity. This guy was able to measure the torsion of the eye. And he used to do so with After Effects. So you stare at a candle for some time, then you close your eyes, you still see the candle. So if you stare at a cross and you close your eye and you look somewhere else, that cross starts to change. And he was there noting. That's amazing, right? Today, it is very difficult to measure the eye torsion with motion captures, right? He was doing this 1847. And he realized that the brain, for any gazing direction, gazing is this. I have a screen, which is 2D. So the voluntary motion is up and down, left and right. That's what it means to gaze. But you see, if I add torsion, almost nothing changes. So if I keep twisting my arm, nothing changes from the perspective of the cursor. But it changes a lot from the perspective of the eye, because if my eye turns, you guys start to turn on the other way. Imagine if you're taking a movie for your friend and you do this with the phone. He won't be very happy if that is a wedding movie. So there is a reason for the eye to stabilize the image that way. And that's what the brain really does. So a few years later, another person called Listing, so these laws go after names of clinicians or physicists or whoever discovered them, figured out that basically, I will explain this picture in the next slide, but somehow the brain projects the degrees of freedom to a 2-dimensional plane in this case. It's a special plane. So you have 3 degrees of freedom, and you need to solve a 2D task. Then the brain decides to project everything on a specific plane or sub-manifold of 2 degrees of freedom, and that makes a 1-to-1 matching. But that's a choice, a neural law. Okay, so now is where geometry kicks in, because when you are in 2D on the plane, but even 3D when you move up and down, well, it's kind of straightforward. But when you go to 3D rotations, things are no longer straightforward. So rotations are difficult for us researchers, but are also difficult for the brain. There are papers that show that, because rotations are non-commutative, right? If I move front, right, back, left, I come back to where I started. If I do this in rotation with a satellite, that doesn't happen. The brain needs to know about that. So this is already very interesting, per se. And somehow I need to tell you about this. You might know, I am not sure. But the way we encode rotations, of course, you can have a 3x3 matrix, which is a lot of elements. But rotations have 3 degrees of freedom. So the most economical way is actually to use a 3 degree of freedom space, which is actually a ball. And this is what this ball looks like, all right? So if I want to represent a rotation, then I can actually have a vector in this space, and this vector is representative of the screw axis, as if you go there with a screwdriver and you try to twist by a certain angle that die, all right? Okay, so from this perspective, meaning from this coordinates become very important. All the orientation of the eye become point in a 3D space of rotations. And if you look at this 3D space, it's really kind of flat. So there are laws like Newton's law, which are very accurate. You hardly go out of it. But these laws are statistical laws. So this is what I call bioware. You have software, you have hardware. This is bioware. These are laws that apply to humans, animals, and they hold with a statistical kind of significance. So you expect a lot of noise here. But for healthy humans, you expect to have any eye orientation line on this plane that from the side is really flat. So this is what you expect when you do experiments, and then you do experiment and see what you find. So just to tell you, in this plane, the red arrow here is something that twists this die in this position. I could have another way to make that little dot get in there, and this is this position. See, this kind of twisting achieves the same task, but has a longer angle. You need to twist for 180 degrees there, all right? So clearly that's a minimum type of rotation, that is non-minimal rotation. Okay, these biological laws are interesting. They are not biomechanic laws. So I have biomechanic laws such as my range of motion for my elbow is this one. If you try to move it harder, I will scream. But for Donner's law, things are different. So people have tried to study head movements instead of eye movements, and they have noticed that in different conditions, I will not tell you much about all these conditions, but this is very interesting. You just look at things as you do every day, and with the same representation, you have this no longer a plane, but it's still a surface, a 2D surface. So the idea that you project down to a lower dimension is still there. It's just that it's not the simple plane you would expect. But very interestingly, if you use special goggles, let's say I have my glasses, you paint them in black so I see nothing, but then you put a tiny hole. So to see anything, I need to keep my eyes pointing straight. So if I want to see anything, I need to move my head, and I cannot move my eyes. So it's a way to freeze my eyes in the head. Now the head, in this condition, becomes my eye. And the way the brain moves the head resembles pretty much the flat plane you used to have for the eye. So this is how the brain keeps switching, and these are all different conditions, which I will not describe for time reason, but if you change the condition, the brain does something different, but still projecting in lower dimension. And for different subjects, you have different shapes. Again, this is what I call bioware. So the names here are different subjects, and this is what happens, for example, with arm movements. Instead of head, now you use your arm to point at things. Or maybe you use your arm to point with the elbow. Or maybe you do another type of pointing. And according to how you use your elbow to point, well, you have very different strategies, and these strategies kind of differ from person to person. So personally, what I see here is a kind of personal signature. The way I walk is different from the way you walk. That's one way to look at it. And now let's come, it's a long piece of history, but now let's come to the early 2000s. We started playing with the wrists, okay? Because I was interested in the wrists, because there were interesting robots for the wrist, 3D robots specifically for rehabilitation of the wrist. And now, well, let's do exactly what I'm doing here. So I'm having this game where now I have a pointer, and I need to point left, up, down, left, right in this manner. And I can only use my wrist. So I rest my forearm, and I use my wrist, my 3 degrees of freedom. And we wonder what happened. Well, it so happened that we found very similar laws. So these are different subjects, and these are repeated trials. And the planes, the surfaces you see here are fitting surfaces. So this is the typical pointing task in 2D space. But when you look at it in joint space, it starts to be this not so flat surface. And this surface is really different and variable for different people. And somehow you can cluster people in some way that you like. There are many kinds of clustering you can try to look at. All right, why am I doing this? Because, well, I started with this technique, so I give a very lightweight device to point, just like this pointer, but a bit more easy to actually acquire. And this is what happens, okay? Subject 1, 2, 3, you have different styles. As I mentioned, there is this robot here that came up after, I don't know if you are familiar with the MIT Manus, it's a 2D robot. That's the second generation, is a 3D wrist robot. But unlike the first generation, this robot is different. It's a bit heavier because by construction, they need to have a big motor at the bottom. So this is a redundant task, remember. A redundant task is a task that you can do in multiple ways. So if the robot makes it difficult for you to move in a certain way, you avoid it altogether. So on the top row, you see free motion for 3 different people with typical human variability. Now you ask the same person to do this while holding this robot, and this is what you get. They are identical, and there is no more human variability at all. So this means that one of the joints is basically locked in place. So it's really a 2D system. And this is what you expect from a 2D system. Okay? So that's the difference between a biomechanical constraint, so I lock one on your axis, and a neural constraint. The brain is actively controlling a law, is imposing a law on the various segments so that you get this kind of behavior. All right. So we say, okay, what happens if, now that robot, the second row is pretty flat, what happens if now we help the robot feel lighter? With some control, you can make the robot feel better. You start to get some variability again and some personal style. Now, we thought that this was very important because those robots are for rehabilitation. And you are trying to hook up a person to a robot, and that robot maybe is not doing what you would like to do. So these are healthy subjects. These are students. The very first experiment is always with the students, right? And the students were affected this way by the robot. So maybe I'm not sure this is what I want for my stroke patient or something like that. So this is where we were working just before I moved to NTU. This was the work done in Rome. Anyway, closing a bit. So somehow, the brain, you go from a larger number of joints, say 3D joints or more, to a task. Here the task is 2D. So in the task, you need to do something, right? It could be your locomotion, by the way. But you have to have more joints to actuate it. And you have 2 choices, or more choices. So the brain seems to impose a kind of intrinsic surface onto which now you project 2D to 2D. What can be different is that instead of having this one on a surface, you just have it in free 3D space. But the risk is that when you close the loop, you don't go back to the initial position. This is actually what happens and can cause injuries. Imagine for a second if you look around the room, up, left, down, and when your eyes come back to the top, they are twisted. That's exactly what would happen if you didn't have this kind of neural control. It would be painful and probably not easy for the brain to make sense of the world, right? People have shown that these things happen even in locomotion, and this kind of planes or surfaces happens to develop even at a very young age, okay? So they can be an indicator of healthy behavior, abnormalities, or neural development. Okay, we wanted to make sense of this from a model perspective. So these are the rotations, this is the coordinates for that. And then we borrowed some discomfort functions from the same cruise that you just mentioned before. That's why I knew cruise, because that's where we borrow. So instead of modeling the muscles, which are very complicated, the simplest thing you can think is a discomfort function, a U-shaped function for each of the joints, where the center is where you are in the middle of the joint range, and the more you go towards the extreme, the more discomfort. That's that simple idea that Cruz actually proposed. And with the simple joint-based, these names, FE, RUD, and PS are names for the joints. I will not go into it, but they correspond to this kind of rotations here. And now you start to have the problem of moving with many possible alternatives, but by minimizing a certain function. And of course, when you introduce a function to minimize, then very easily you get a unique solution. Let me know how I'm doing with the time, because I might speed up. I tend to go. You just let me know, I will speed up in case, and we can continue tomorrow to discuss it. You signal. OK, thank you. So, and now we go to this problem, posture. So what I was just saying before is that if you introduce a function, that could be a potential function, an elastic function, any potential that you want, gravity and so on, any potential you like. If you introduce a scalar function and you have many alternatives, then you can simply minimize that function and you will come up with a unique solution. That gives you posture, equilibrium. Fine. That's simple. But how do you reconcile posture and movement? Somehow posture means I stay put, and movement is, well, no, I need to move. So somehow these two things seem to be in contradiction. And there is a lot of interesting literature, Celan in 2000. They proposed what they call the velocity box. And that's very interesting because if you have a fixed surface, this is also called as a holonomic constraint. That's just one word. If you are not familiar with it, don't worry. But if you basically fix the law, if you fix this surface here, you are basically stating that all the variables need to be on this surface. That's what you're telling there. And that would be very rigid type of constraint. You're there, you cannot do any elsewhere, just like the robot would constrain you on those surfaces. Okay, mathematically, you could just take the derivatives. You can differentiate the constraint. And now, these become coefficients. So now you have the same thing, but with a more general form. Seems that it's just a mathematical trick and so on. But now, the important thing is that if you pick random A's, random coefficients, instead of specific coefficients, you no longer get a surface. This is a problem of integrability. If you have a constraint and you try to integrate it, only some constraints are integrable, okay? And that's exactly what this method allows. So this is a nice method because it allows for the constraint to be there, but it also allows for the brain to change the constraint. So maybe this is a simpler way for these coefficients here are a simpler way for the brain to actually tweak this constraint. Because we need to also account for the experiments where we go out of the constraint. We are not always there. So we are now there and trying to understand what's going on. And we have a bunch of frameworks that are available from the literature. So we have any minimum principle, minimum, maximum, minimum, whatever you like. These principles are easy to implement, but they really are not compatible with Donders. You don't get holonomic constraint when you have redundancy. Then you have the things I told you, but this is also not so good because I don't know how to reconcile posture and movement. There are other things that I have no time to discuss here, but these are available frameworks. And we found that from literature, there is this very nice, simple principle that helps us a lot. I've been playing with this principle for a very long time. And it's somehow very simple. It comes from early studies, year 99, 2000. Watch out, this is very controversial law. If you talk to any other colleague of mine, they might not like it. It's controversial whether humans apply it. But in the end, we are engineers, so we implement on the robot whatever we like. So the idea here is very simple. If I need to lift a book or something, well, I need to activate my muscle to do this movement. Now, there is a part of the activation. Imagine that U here stands for the muscular activation. There is an activation that is needed because anyway you know gravity exists. So this U0, U0, is the activation that I just need to stay in this position. But if I stay in this position, nothing happens. I still need to move. So you need some extra activation. And that's it. That's the principle. The principle says, well, the brain really minimizes or any optimal control law that you have is applied to the dynamic part of you, not to the entire you. And that's a very simple but powerful principle. And we've been using it ever since. So now a few words on equilibrium. These are nice books from the 80s. I like to read stuff from the 80s. And if you want the detail, we can discuss, and they are in very recent papers that our group published recently. And maybe, I don't know, if we can figure out a way to use it for insects, I would love that. I really would love that. So here we'll go slightly faster just to show you what it's all about. And if you think it's interesting to you, we can discuss tomorrow, and you let me know about the timing. But the idea is very simple. Whether you have a leg or a pendulum or an arm, it's going to be comprising mechanical parts, elastic parts, and some control. In this very simple thing, this is inverted pendulum. I would like to invert a pendulum. This is the simplest example I could think of without becoming very trivial. So this is the pendulum, and you all know how the pendulum works. There's some gravity, so the pendulum would like to stay down. Your agent is a robot, so all you control is the XY position of the robot, which is this red cross. And the interaction, because the interaction is the problem, right? You work with foot contacts. How do you account for the interaction in your theoretical framework? This is the way we do it. We learn to do everything with springs. We invent very strange springs, but we use springs, nonlinear springs or linear spring. You can start with linear ones, and then you complicate it later. But basically, you can attach a spring to this guy, and now that's the only way the robot can lift the pendulum. This is a year one physics kind of problem, and you can find the equilibrium. It's not very difficult. But in slightly more general terms, it means that you can come up with a potential function. This potential function has gravity of the pendulum and the strain energy of the spring. If you have more springs, you just put everything there, sorry. Sorry, I don't know what happened. Sorry, wrong button. So you have a potential energy, W, and there are two sets of variables. They are not different, but the U variables are the ones you can really control because you have a robot, you can program it. What we call a Z variable are things that you cannot control directly. So the pendulum, you cannot touch it. You can control it through the spring, but not directly. So you have your ROS package that tells you how U works, and for us this will be the DMPs and everything. And only by moving this one indirectly I can move the pendulum. That's the meaning of it. So we just look at the problem long enough, and we try to understand how to split variables between what I can control in my problem and what is a secondary type of control. But other than that, it's just a regular potential function. And we are interested in the equilibrium. This is a fancy way to say I'm looking at a zero for the internal forces. In almost every mechanical problem that is not too trivial, you'll find multiple equilibria. So if you just look at the equilibrium conditions, you find at least two. In fact, there's a third part which is unstable, which is when the pendulum is right up. But now, all these possibilities are there. You can discretize the problem as you want, so we go with graph theory there, but it's not important. What I want to highlight is that you split the variable into Z and U. The U variables are your robot and are at the bottom here. So this is UX and UY. This is what you can control with ROS. And the other variable, I call it alpha, but it's basically the angle of the pendulum, and is your Z in this case, is whatever the system, the environment. See, the problem here is the environment. It's easy to model the robot. The issue is the environment. The environment decides to do whatever it wants, depending on the geometry. And you end up with this kind of equilibrium. Now, if you are doing quasi-static motion, your stick insect is probably under quasi-static assumptions all the time. A horse that gallops is not, but the stick insect probably is. Now, the problem becomes going from A to B without flying. So with this kind of problem, the robot will understand that the only way is to go through this point where these two surfaces intersect. That's actually the point where you go and touch the pendulum from the bottom. So somehow, might sound trivial to us that to lift a pendulum, you need to pick it. But here, I'm not there telling the robot. The robot discovers that the only way to get is through that point. And to me, this is something interesting because this is something that we take for granted. Okay, I'll go a bit faster, but we have used this in many ways, and if you're interested, we can guide you. But this is my student, Yan Ling, has been doing this work. We've been placing books into the bookshelf. The issue with the bookshelf is there is always no place. It's a crowded bookshelf. So any geometric algorithm will tell you there's no space, sorry, come back tomorrow. But when it's a human, you don't care, you just stuff your book inside. You press a bit harder and the book will fit. We would like the robot to understand that without telling much. So this is what's happening. You have the books, which have some elasticity. Again, there's a lot of elastic components. And this is the book that you are supposed to stack in. The first attempt, here we use DMPs for the controls. And then we use black box optimization to get like evolutionary type of algorithm. Simple stuff. So the first attempt is to go straight and just push this book inside. Of course, it will not be very successful. But very soon, meaning very few trials, just like your few steps. Because the good thing of your methods is basically similar to the DMP. They have just a few parameters. So it takes very few trials to get something optimal. Somehow, with a few trials and iteration, the robot, in a sense, learns that you need to wiggle your book inside. So you need to come in with a corner to make more room for it. We did not program this behavior. This one came out. There is a theory behind. If you're interested, I will guide you. I will not go through this. This is the theory. But all I want to say, there is some more mathematical aspect there. And what we have is a Riemannian metric. With this metric, we turn a motion control problem, motion planning problem, into a manipulation planning problem. So this thing that you see there, G, comes from the potential. So you set the potential, so there are no choices by me, is the problem. Very often when you do optimal control, you need to come up with a very clever function to minimize. That's an art, and it's fine. But this one, this G, there's nothing that I make up. If I have the potential, I have the G, and here I need to square it. That's it. So we like this because it's principled. And I'm going to conclude. This G, whatever it is the second derivative of a potential, which means it's a kind of stiffness. So in the end, we are going large circles in the theory, but we ended up with stiffness, which is a bit what you mentioned as reflexes, the very first connection with the environment. If you go rigid on a wall, you'll be very hurt. Okay, so you need to adapt your stiffness when you deal with a wall. And okay, this one will take too long. So I'm skipping this, but if you like this slide, I will tell you later. So I just want to tell you something more experimental. One, the stiffness is important for us. We do these tasks. We want to know how humans stiffen up one joint. It's not that difficult. Okay, it's challenging from the level of noise because forces are noisy. But you basically measure torques, you measure motion, and then you fit. That's not very difficult. So you get some stiffness parameter that you can use in your robot for impedance control. So 1D is fine, just signal processing, but fine. When you go to 2D, things start to be complicated because now rotations are non-commutative. So if you start to take derivatives, you get Hessians, so second-order derivatives, that are non-symmetric, and that is a problem. So again, story short, we want a device that tells me about the stiffness of my wrist. So there is actually a clinical need behind. I want the therapist here to move my wrists, and this device here measures positions, so rotations, and torques. And by sensing position and torque, you should be able to estimate stiffness. And there are many difficulties due to the rotation. But this is what the clinicians want. So they want, in the end, a kind of ellipsoid, because stiffness is supposed to be an ellipsoid in the end. And the eigenvectors are really related to muscles. Human wrist has 5 muscles, and the direction of that ellipsoid really depends on the physiology. Even worse when you go to 3D stiffness. So 3D stiffness is very complicated. Clinicians like to use these anatomical coordinates, or cores. Engineers like to use these different coordinates that I told you at the beginning. And mathematicians hate all coordinates. They really don't want any coordinates. It's very hard to talk to them. So the problem that I'm hinting, which I will not describe much, is that stiffness has very strange behaviors. Stiffness has very strange behaviors, and only kind of behaves well at the equilibrium when you don't have this term. And this is the problem of Cartesian stiffness. So it's stiffness at the end point. There's some geometry behind that I will not go through. But in the end, you see, you start with a potential. SE3 is the space of 3D motions. And you want to kind of work with second derivatives. There is a lot of technical difficulties. And next time we meet, I'll tell you about that, because it's a work in progress. But the idea is really this. Now we are doing an experiment with our robot. We move our robot. So we program every joint with a linear spring, simple stuff. Then we move the end effector, and we perceive a stiffness. Now we would like to find it out from data. The data are terrible. Torque, force data are always terrible. And the idea now is to collect all the poses, all the wrenches. We call wrench the force and the torque together. And we try to fit this equation because it's 3D rotation, a very weird equation. And the idea is to come up now with the potential, because this is an estimate of the stiffness, which we think it's important for skills. Anyway, I'll stop here. I thank you all for the attention and for the invitation. Thank you very much.
Great. Thank you so much for nice presentation. So now we have a coffee break for 15 minutes. Yeah. So, but before that, I'm not sure that anyone has any question to ask, but we can just like take a break and discuss with him, or you want to like ask here just one or two questions? Anyone from the audience? So if not, maybe I introduce once. Can you summarize the short description of the donor loss? Okay.
Basically so that is specific to the eye movements, but in general, it's important to understand what the task is, because these laws change if you change the task. If the task is gazing, and the eye only does that task, the eye doesn't do any other tasks. If the task is gazing, it's a 2D task. It's like me moving the point. But there is a torsion that is still free. If I keep twisting my arm, you shouldn't be seeing any difference in the pointer. But it makes a difference for the brain, because if I have a camera in my hand, you will need more time to process all that. So Donner's law basically states that independently of the path you take, when you come back home, the trees still look vertical. You see, there is a reason why when they mount telescopes, there is one axis first on the ground and the other axis there. Because when you move around, you still want to see vertical trees. But there could be a different choice. You could have the first axis to be horizontal, the second up. So rotations are very tricky, are very, very tricky. And people who work with the optics, it's a bit familiar. And for the brain, it's very important, because we move eyes around. It takes time to compute. And at the very least, I would like my image to stay the same. If I need to compute, I need to recognize faces, but these faces keep twisting in my retina, it will take way longer. So some people suggest that this is one of the reasons for implementing this law. There might be other reasons as well, but definitely this makes sense from the information perspective. You want to have a stable image as much as possible. I don't know if this answers.
If I understand correctly, it's like you translate, you mapping from 3D movement into the 2D.
Well, okay, sorry, maybe I rephrase this. So you have 3 degrees of freedom, but your task is only 2. The third, which is torsion, will have a consequence on how you see the image. Now, if the purpose is to keep the images steady, then the torsion is fixed. It's a nonlinear function of the other 2. That is what is called holonomic constraint. You saw in some slide a function f of all the joints. So you have 3 joints, fine, but if you put a function of the 3 joints equal to 0, you are killing one of the degrees of freedom. So you are only left with 2. And that is really what the most general meaning of Donner's law could be. So every time you introduce a constraint, you reduce the degrees of freedom of the system, like in robotics, right? But this is a neural constraint. That is not a biomechanical. So if I lock one joint, because I go to your robot and I lock one of the joints, now you bought a 6 degrees of freedom robot and becomes 5 because I was too bad and I locked it. But that is the brain that decides, but it doesn't often lock only one joint. It sets a constraint of all the joints. So another way is you have a robot, but now you need to carry a soup. Try to carry a soup like that. You won't have a job for a long time if the soup is, the hand has to be horizontal. So when you move around, that's a constraint. And of course, it's not, sometimes we don't do a good job and the soup spills, right? But somehow we train ourselves to do this motion and carry the soup so that this axis is always vertical. That is exactly one of the constraints you can add. Yes, I have 7 degrees of freedom, but if I do this one, I won't have a job if I'm a waiter. Having this constraint makes it easier to come up with a trajectory. Because now you have fewer degrees to work with. But if you just fix that one, then why did you buy a 7 degrees of freedom robot? You wanted one extra thing. So if you change task, now you will change. So that is the beauty of the neural constraint. It's not a biomechanical, it's not a fixing. Otherwise, just buy a 5 degrees and you save time. You want all the ability to move as you want, and for each task, then you specialize your constraint.
Yeah,
That's one
that's
way.
why you put a constraint for a certain task.
So this constraint carries some optimization. So that's why we can predict them with simple optimal control, because probably even having the trees always straight, that's a form of optimization. You optimizing the similarity, the entropy of the information. Whatever, you can twist it as you want. But there is a concept of optimality in this concept.
Okay.
The humans are very complex, and then you can start to, okay, this is that's why there's no you are learning some AI machine. That is where you can do it. If you only buy a new robot, what do you do? You train. If you have trained your AI with a certain type of order, that will do it. Here is where I don't have here. But where I'm heading to is I'm not the only one because there are things in physics that nobody really talks about. These are things that don't change inside of it. Whether you measure with a motion capture, with an eye movement, with other things, there are things that never change. This is what I said.
Okay. Yeah.
I think this is very interesting in the sense that if I understood the concept correctly. So basically, if you look at the joint space, you have more redundancy in the joint space. But to achieve a certain task, the system bring that into, when you talk into task space, the task space is where you interface with the constraint environment. In that way, you see the graph where you can look at the mechanics, you can less variability. That's because of the constraint of the environment that limits the variability of that. And similarly, when you want to carry a certain distance, the system try to optimize the constraint such that it maximizes efficiency for the task that you can produce. So bring back to human machine interaction. What do I think that's interesting that let's say we as a human, we show how we write, correct? This is where we put ourselves to the constraint. Why in the robot parts, the robot also need to put itself into the same constraint. So this means that basically we try to go into, if you want to achieve the same task, we're going to put ourselves into the constraint such that when we look at this constraint task in adjustment, you can repeat the adjustments, and from that you can map it back to the joint state of a certain system, whatever it is.
I skip one slide, but I can show you based on this. Because for time, I will make it out. There is this very simple model. This slide is this slide. Maybe I can do this. So look at the diagram. Now the main. So nature always solves the system. Now, if you think of joint spaces have so many, should have a chain, with a particle chain. 50 points, I don't know.
Yes.
But you only need to move in maximum level. How do you solve? If you take a chain and you move in maximum, the chain is solved. How does it happen? So you can then start to say, okay, let me prove them. If you ever then do the chain with the slider, but you have them, so you move them on very easy. That's called the so you can take that one as a chain. There you are in mind. What we do is, not only that, also that's why in the end we all boil down. Because if you only do that, no reason to do that. But if you put people things that are the same, it's like the APL. APL has many joints, you take the endpoint, you fill up points. And that is the same thing as shown in the elastic potential mathematics. So that diagram, I apologize, not here, it's not properly explained, but I can explain more. But when I was going with
Okay, it's okay. Maybe we need to go out because the coffee break is waiting. Okay. Okay. Outside. Yeah. Yes. ล่าสุดครับ
ออกมาก่อนงานท็อปที่แชร์2 วัน
จริงเหรอแล้วก็ชื่อการท็อป
เดียวกันด้วย
อัลฟาเกรดอัลฟายูอ๋อเรียกเข้ามาเลยไหมจะได้แต่เราออกไปช้านิดนึงไงเราออกไปช้านิดนึงก็เข้ามาช้านิดนึงนี่พวกกันเดี๋ยวส่ง
ตัดเปิดช่องให้ตัวเองเปิดช่องให้ตัวเองไม่เขินไม่อาย
คนจัดเนี่ยคนจัดทำอะไรก็ได้
ไม่มีอะไรมาแบบ
แต่งเทียบของเรื่องถ้าจะเรียบร้อย
ตัดไปเรียบร้อยแล้ว เราไปกินนานยักษ์มันอยู่ที่ไหนอ่ะมันตัวที่ไปลุงร้านนี่มันมีร้านนี้นะอร่อยดีบาลามีไม่เจออะไรที่นั่น
ลองดิส
ไม่
แท็
ได้
กกับคุณเองที่เราไม่ได้ที่นั่งไม่ได้
มันต้องไปแบบ2 คนแต่ละที่2 คนแล้ว
น่าจะฉันโก้ใส่มาเนี่ย
เพิ่มความเย็น
คนมันน้อยไง
จริง
เคยพูดแบบเวที
ท็อปได้ยัง
เคยเหรอ
ผมกินไป6 อันแล้ว
เฮ้ย
คนเดียว
กินกันหมด
เติมของก่อน
เฮ้ยพี่ยังเหลืออีก1เลย
กินทั้งหมดเลยพี่จะไวมากเลยนะครับพี่จะไวมากขึ้นลงเลยก็คือให้เรียนรู้ใครก็ได้
ใช้คำว่าใครก็ได้ด้วยนะ
ได้
ไม่ได้มีแบบสิ่งที่เราเดียวได้5 นาที
วันพรุ่งนี้ตั้งปูเพราะวันพฤหัสครับกับเช้าอยู่กับใช่อยู่กับเรียนปูเขายังแบบหาเครื่องเพลงง่ายๆเจอใครคุยงานก็ไปแล้วก็คุณวาง
ผมเลยงงว่า
ก็มีรันไงมีรันคนหนึ่งแต่คนหนึ่งก็
ก็เหลือคนเดียวเลยผมที่ผมกินเนี่ยก่อน
ตาม
มา
ไม่มี
เอาเมื่อวานก็ไป
มีแต่คนรอฟังออกมาเทรดนะครับนี่ก็ได้เป็นคนรอฟังเลยนะครับเพิ่มชื่อข้อมูลนะครับเราไปอัพดูที่อัพโหลดในเว็บจะมีลิงก์เข้าไปจะมีเข้าไปแล้วก็มีซีรีส์คนละประกาศแล้วก็เพิ่มแบบมันจะมีทำเองเหมือนหน้าแรกกับที่พี่เคยมันก็จะโชว์ว่าแบบไอ้ประกาศออฟฟิเชียลใหม่จากเพิ่งมาเปลี่ยนใช่ไหมพี่ก็เลยแก้ใหม่ไอ้ข้อมูลที่อยู่ใน Facebook อะไรมันก็ไม่แม่นหรอกแต่เดี๋ยวไอ้ตรงในเว็บอ่ะมันอาจจะมีชื่อนั่นอยู่เผื่อท็อปเอาไปใช้อ้างแบบอ้างเราแบบ Okay. So maybe we continue to the last two sessions from me and from Top. Okay. So for me, maybe it's quite a short, like 15 minutes, and for the Top, it's the rest of the time, maybe more than 15 minutes, but we expect that for Top, roughly at least 15 minutes. For my topic is about neural control for lower limb exoskeleton. I think most of us familiar with this. For the one who not familiar, it's okay for me to disseminate this information. Okay. So mainly I'm focusing on the human gait or the walking. So actually the walking is a complex behavior. So the movement of the trajectory of the walking is in 3D. So you need to understand the plane first. But lastly, I focusing just only on the sagittal plane. Sagittal plane means just only the back and forth in the simple term. But actually when you walk, you also rotate yourself like this as well. And also you rotate yourself like this as well. But the sagittal plane is just like this condition. And for this walking gait, normally we call the big phase, just only two, it's just stand phase and swing phase. Stand phase in the normal human, both women and men take around 60% of the total period of time. Like when you stand, it starts from the foot, we call it heel strike, and then until the toe off. This we call the stand phase, and then come into the swing phase, and then go back into the heel strike again. This is the whole phase of the walking. Very simple. But in terms of the real musculoskeletal things is more complex because it's dealing with multiple muscle at different state of the time. But we are not going into that. Just want to tell you that I'm focusing just only on the very simple planar movement first. The core function that we want to derive in our control is just very simple to three things. The first thing is the rhythmic pattern. Actually, walking is not just only rhythmic. We can do the just discrete pattern as well. Like the rhythmic means you just repeatedly walk or running, right? But discrete is just like when you go up the stair. It's just maybe one step and then you stop, something like this. And this one, we want to gain the control that we want it to be more robust. Actually, you can do many model-based control and you put more constraint and you derive that it's robust already. But there is other way. If you apply this control on neural control base, there is a guarantee that is quite robust in terms of disturbance rejection already. If you familiar with the term of limit cycle, so when you have this kind of equation, it will kind of cyclic itself all the time in mathematical sense. And then when there is external force come in, it rejects. And rejection means it will deviate from the certain trajectory a bit, and then it can drag itself into the normal trajectory by itself based on their mathematical function. This is what the robustness that I want. The second thing is not just only the rhythmic pattern, we want also the individual pattern, because each people walk with different pattern for sure, for your hip, trajectory, knee, and ankle. And this one, we want to acquire the individual this pattern for each task. And finally, because if you have just only the fixed trajectory, right? But this robot is not just walking alone. We want it to work with the human also. That's why we want some influence from the human into this robot. And if you like fix the position control to it, maybe it's not good. You need some relaxation of the signal in order to let the input from the human to influence the robot or the trajectory signal as well. We call this one compensation or relaxation of the signal. Okay, and then come to the rhythmic rhythmic part. So as Ajahn Paramesh said, we have one famous small neuron network called CPG. This CPG can generate the signal like a sine wave, but it's not exactly the sine wave, but just rhythmic signal. And we have a special one. We call this one AFDC, or adaptive through fast dynamical coupling. We can separate it into two parts. Quickly describe you what this CBG do. This special CBG do. The first part is like you send the external signal come into your neuron. This is the first part. The second part is the part that it generates the signal by itself. For the first part, if I have light signal like this come into this neuron for the certain period of time, this neuron will activate for a while, and then for the second part, two neurons will activate, and when they activate, they try to learn this kind of pattern, this kind of external pattern. What they learn is the frequency of the signal. You can see that first the frequency, internal frequency is just, let's say, when I plot the signal is like this, frequency is like this. Maybe it's starting from the 1 Hertz, and then when the external, when they're learning the external signal, it comes into those external signal frequency. It's like it go down into the 0.5 Hertz. This is the way that this network do. It just learn the external frequency signal. And then when there is no external frequency, there is no external signal, the network still retain those frequency. It's kind of remember the frequency by the network itself, and then it still generate the signal by itself. Okay, if you want to look deep into the equation, the main keyword for learning is the Habian type learning rule. It's kind of you multiply many parameter and variable together, and okay, you can look further into it. And those parameters will change one, combine and change it into the one parameter called phi. For this phi, and then you have a metric to govern this phi into and transform it into the weight of the network, or W, each W as I circle here in the blue. And phi also can be defined like a internal frequency of the CBG as well. I call this one FCBG. If you look deep into it, at this point, the unit is not the hertz or cycle per sec, but actually it's just cycle per iteration, because this whole equation is just a numerical equation. So the unit is just cycle per your computer iteration. So it's not the real frequency that you can use directly when you apply into the real robot. You need some transformation to make this unit to the correct unit that you can be used outside as a circle per sec. I'm not go deep into that one, just told you that what is it. And there is like some other equation to govern this changing of the weight as well. And finally, if you combine whole thing together, you can write a metric to govern the whole CBG. And it's just simple neural network that you have the activation neuron, and then you pass the activation neuron to the tan H function, and then you use the output into the H out. Okay, that's for the rhythmic pattern. For the pattern itself, we use the one kind of neuron version of the radial basic function. The normal radial basic function is just kind of you use in short term it's like a weighted linear combination of weighted combination of the kernel function. Your kernel function can be like just only Gaussian or other kind of kernel, but basically we use just Gaussian function or maybe very short like a delta function, and you combine this one together to compose into any kind of signal. But we can transform that mathematical into neuron, implement it into the neuron-based terms. So, and we can have like different set of radial basic function for different hip, knee, or ankle. Those different sets will be try to generate different pattern for hip, knee, and ankle. How to use this one when you combine it with CBG? So you have two input from the CBG, H0 and H1 come into the to the IBF network. And then from this one, you put into we call this one two variable Gaussian function. And then this Gaussian function will produce like this, like the graph below here. And we select, we use the whole one cycle for the CBG to construct this kind of kernel, multiple kernel here, 1 to k. And then from this one, you can use this one to generate the output, the result for each hip, knee, or ankle already. But maybe the first result is not good, so you need to do some there are many techniques, but very simple technique is just to do the error-based learning rule. It's just, you just minus with the target, see if it's close to the target or not. If it's not close, you just use that error to tune back to the weight, the output weight. That's it. That's the way that you learn the whole thing until it converges into, the result converges into the target pattern. This is the way that we use this RBF, neural network RBF. Okay, and if you want to see, graphically see what is it, it's like you have multiple, as I told you, we have multiple kernel here, and then we sum up with different weight, and then you combine it and you get the final result. So if we put everything together to drive to be a control of the exoskeleton, I call this one mid-level control. We have rhythmic discrete, or we can generate this key or rhythmic signal here as our CPG. And then we connect it into the RBF or radial basic function to generate pattern. So, and then we get what we want. The first part, we get the individual walking frequency. And the second part, we can shape to any pattern that everyone, for each individual. And then we send this command, the pattern or the target, the driving pattern to the lower level or just only PAD, position control. And then we drive the exoskeleton. But I think we forget one part. This part, if you look closely or fast, it's just only the open loop control. Where is the feedback? Actually, my control, there is no feedback yet. But another point is that if you remember the last slide, you need like a target first before you can activate this neuron. That means when you activate this, you need to have like a learning from the demonstration step first. It kind of you record or you let the expert or the people train the robot first how the pattern or the walking frequency of those individuals look like. And then you let the neuron, or you let your control network learn each parameter. Like when you walk, you use the hip feedback. You put it back into what they call is FCBG, right? If you remember the first slide, this hip pattern, right? The CBG, you learn what is the frequency. It's kind of like you translate you do the Fourier, but it's not in the like offline frequency domain. It's kind of you do the online time domain Fourier transform because you get the hip feedback and then you translate it into the frequency. So you know what is the actual walking frequency of the people. That's the one thing. The other thing is that you just read the target trajectory from each hip, knee, and ankle, and then you just let it into the RBF. So the RBF know how to it's kind of encoded those feedback into just weight of the network. And then when you want to active it, right, you just have the frequency, and then you can generate the correct frequency by the CBG, and then you use the weight to reconstruct back the correct pattern of each people. This is the way that we do the control for the exoskeleton. The good point is that maybe you store less information because you embed it into the weight, right? Instead of just record the whole thing and replay it. And when you do like this, maybe you can tune parameter or you can re-engineering some parameter easily. The other thing is that maybe if you want to do more things, because you embed that information like complex information into just weight of the network, you maybe can do more complex things from those embedded information as well. Like, for example, if you want to classify a walking pattern, maybe you embed it into the weight of the RBF already. Maybe you can classify based on those database of the weight. Something like this. This may be a bit benefit of this one. And the other thing is that you can monitor the frequency online. This is another benefit from this kind of network. So maybe let's see the result. The first you need to learn. For example, this walking frequency, I let the subject walk on different speed of the treadmill, and then we record for each speed. And then when you do the exit, I let the treadmill run continuously, and then we slowly change. But of course, we don't have the high level to switch between speed. We just use the people to switch the frequency, the speed of the treadmill. And then the EXO will also, we need to switch correctly as well. But what I want to say is that those speed is correspond to the speed of the treadmill. It's synchronized to each other. If it's not synchronized, the people cannot walk like this continuously. The people will fall or slip out of the treadmill. This is what I want to show, that the whole loop is working. If you have high level intelligence, you maybe switch the speed online. But right now it's just manually switching. Okay, another thing is that it's not just the cyclic movement. Okay, the thing that I want to show is that you can learn different patterns for each leg as well. For example, in the stroke patient, right? Maybe the patient will walk different speed for each leg in the stroke patient or different pattern. So this kind of algorithm can also capture different pattern for each leg as well. And then at this video show, we have split belt treadmill. Maybe the left side is very fast, the right side is very slow. And then we can capture this, and then we can, when after learning, when you deploy the algorithm again, so it can assist the patient to walk on the different speed of the treadmill as well. Not just only the cyclic movement, but also the discrete movement that we can generate as well. If we let the exoskeleton learn the discrete movement when you're walking up or down the ladder, so we can, and then after that we deploy it, let the exoskeleton assist the patient. We also get the successful result as well. But you need some technique to kind of change how the rhythmic pattern into the discrete pattern in order to achieve this kind of tasks. Okay, and those, it's just the rhythmic pattern and also the pattern itself, right? Coming to the compensation or relaxation of the signal. We want to get the interaction from the patient or the subject coming to the robot, right? So normally we use the position control, but this time we use another control called impedance control. And what is impedance control? Impedance control is just you translate from the motion or the trajectory or the movement into the force world with the parameter like a transformation metric. We call this one C or the impedance. And then normally impedance is not adaptive over the time. But one of our researcher, he focusing on how using the adaptive online impedance control. So that means the C is adapt according to the time. And what is the real equation? The real equation is that you have the assistive torque, right? You have, if you look into the equation, it's K time the error. This error is like a position error, and the other one is D time the velocity error, E dot. And then you have another term called forcing term. So what is this one related? If you look, roughly, it looks like a PD control with the adaptive parameter. So the first parameter, it related to the stiffness because it linked to the position. The first parameter we call is, the second term we call is damping because it related to the velocity. And the first term is interesting because it used to define other term. So for the first, and if you look into the equation itself, it's not just the scalar, it's the vector things, because we want to solve this thing all together for the sixth position of the motor. Also, KD also a vector as well. And the forcing term, you can look to the paper later, but they define like this. First, we define the epsilon E, epsilon T here. So it just, you use just error plus the velocity error term. And then you can define the forcing term here like this. And this one, if you look roughly, it's just like you have a nonlinear term to time your epsilon term vector. And with this why you use this nonlinear? What I understand is that you want it to respond very fast when there is when you have very high error rate, and then you get the high value of this term. After that, you have this term, and you define further like adaptive term also, like grammar. It's just the reciprocal of those square equation here. So and the term is look like this one. So but it's the same thing. Just this one is that ET/FT is just like a vector with some parameter that shape your length of the vector. That's it. And they also define this KD and K and D term based on this forcing term as well. And okay, not just only this is the normal online adaptive impedance control, but in our case, we want to add more term. We call this one gravitational term, compensation term for the gravity. See, we also add another term called this term. We can interpret this in another way, like the first two terms, we call this one feedback term, because you get the feedback signal, right? But the second two term in the letter, we call this feed-forward term, because it's like you model it a bit, and then you use this one to manipulate your final torque. That's why we call this one feed-forward. It comes from the forcing term and also the gravitational term. So the whole block diagram is this. We implement this kind of online adaptive muscle here with gravitational compensation here to get the closed loop torque control, and then we can let the intention from the subject into the control. Let's see the one example. So if you walk like just only normal trajectory control, right? As I told you, if it's not synced, so the patient cannot influence the exo. The exo will continuously drive you at that speed. If it's not synced with the treadmill, so it's out of phase, and then the patient may be left off the of the treadmill. But if you use the proposed control here, so during walking, the force from the patient or the subject can influence the movement of the exo as well. And then and also the force from the treadmill as well can influence the movement of the exo. So when the whole thing, when you receive the information from the environment, right, and then you can change the internal system, right, so the whole thing sync, and then you can successfully walk on this dynamical situation successfully. And you also have the compensation from the gravity, right? So when you walk, you feel like less resist. If you don't have this kind of gravitational compensation, maybe you have more error, and you can get those weight from the exoskeleton itself, and then everything may be not that comfortable. Okay, not only just those are my part. We also have another part, and my colleague part. We also have another part, not just only mid-level and low-level. We also have one guy doing about high-level control as well. This high-level, we're focusing on classify the different activity based on the data movement data that we have. The first data that we use is the IMU, just the movement. We have a 3 IMU put into different position on the body, and then we want to classify this IMU movement. And our colleague mapping this IMU signal from time series into the spectrogram, and then with some additional statistical information add into this one, and we pass it into the convolution neural network. And then one key point here is that we use the self-attention mechanism in order to better improve the accuracy of the classification step. And we got successful, and I can show you some demo regarding this work. So I'm not sure I can quickly go into this one or not, but we let the whole subject wearing this IMU and also the knee exoskeleton, and then okay, I'm not sure. Okay, and then it's just like successfully walk on the different. Let me. Okay. So it's successful. The subject can walk on different situations, like from sit to stand, and then walking up the stair, and also walk on the treadmill. And during those kind of activity, the algorithm can classify correctly what is the activities. You maybe get some delay or some error, but roughly you can achieve like 80 to 90% accuracy. And this is the whole thing is online. So we pre-train the model first, and then when we deploy it and do the online tuning to successfully get the classification. But there also is like a weak point as well, because if you learn the new activity, the network tend to forget the old activity. So we need to solve this later in the next version. Okay. So the next thing is that not only just high-level algorithm, we also have like the guy who do try to focusing on how to do the good hardware, and we want, as you see, the exoskeleton itself is quite buggy. It's quite a big one. So we want to reduce it into modular things, and when you reduce it into the modular things like a knee exoskeleton, you will face many problems like how to hang it, where to hang it, and can it be really good can it be like supportive enough and attach closely into the human in order to help the patient or not. So one of our guys developed the whole structure to be adjustable to every size of the patient, and also change from the traditional strap into the more adhesive version in order to help it lock closely with the patient leg. And here is the result. So you can see from the right side is that the traditional strap. So when you walk with this kind of knee exoskeleton, slowly it will shift down, and slightly loosen from the body of the patient. But if you use our design solution, so it will tie closely with the knee of the patient. With this tight lock, so when you drive the control, so the patient gets better movement. And not only that, if it loosen, right, so you need high torque to drive it. But if it like very fixed, so you can drive it efficiently. Okay, and not only when we done things in the lab, right? Another thing is that we want to connect to the outside. We have we want to test one algorithm and the whole system with the clinic as well. So we have experience once when we try one algorithm with two sites, the real clinical sites. One is at the orthopedic department at the hospital. The other one is with the physical therapy. Okay. Lastly, the whole idea here is just try to let the therapist familiarize with the system, and also we want to evaluate our control as well with the clinical variable like VO2 max or metabolic consumption rate, and also the EMG signal, the muscle activity. And also some comment from both patient and also from the user, both patient and the physiotherapist as well. What it be like to use our system and our control. So far, it's okay, but it's too tedious and it's a bit difficult to interpret the whole things. But lastly, we get a comment that you need to reduce the size and design more small or more portable version in order that patient want to use. And another thing is that if your adaptation is not intelligent enough, so maybe it's confuse the patient itself. Like the patient want to adapt, the exo want to adapt, and there is a delay, so the adaptation is not that sync. This is one key message that we get from when we test. But for the VO2 like metabolism size, lastly is when the patient wear the exo, so it reduce a bit of the metabolic cost for sure. But if you compare to the bare walking, it's like no device, right? So you cannot compare that because if you don't wear anything, right? So your metabolic cost will be the lowest for sure. But if you need to compare when you wear things with two different design or different control, and that's the baseline that you can compare. But so far it helped. It's not just you wear things that's really buggy and it's not help. It's it's help. That's the whole thing for me. Okay. So maybe next. Or any question can ask me later. I think there's no question because either I talk confusingly or everyone understand correctly.
So, good afternoon, everyone. My name is Ratanapol Chaisan, a PhD student from Interface Lab. Today, I will present my recent papers named AlphaGrad. The full title is Normalized Gradient Descent for Adaptive Multi-Loss Functions in EEG-based motor imagery classification. So, traditionally, we are familiar with the single task learning for neural networks. For example, we design each network for each task. For instance, we want to classify left and right motor imagery. We want to design a specific model for that. And when we change the data, for example, in another task, like sit or standing motor imagery, we need to redesign the new model. Yeah. But today we have more resource to compute, and then we can design the model that do multiple tasks in the same time, like multitask learning. We can use multiple data sets, and we have like output from different tasks in the same model with these shared parameters. So like our previous work named Min2Net. It is the first model that employ multitask learning in EEG classification. We design with 3 tasks to help to classify motor imagery EEG. Like we use autoencoder to encode the EEG data to compact signal. And another module is we use deep metric learning or triplet loss to like make the EEG from the same class, a feature of EEG from the same class go together and separate the feature from the other class. And these 2 modules help to we make the classification of left and right hand side, left and right motor imagery. Another work from other teams that they design the model that similar to our works, but they just use 2 modules for 2 tasks, like center loss for separate the other tasks, and it is help to bring the same class come together and help to classification. This work not use just like simple EEG. They filter the EEG into multiple bands. For example, like from 0 to 4 Hertz, 4 to 8 Hertz. So when multitask is benefit for motor imagery EEG classification, but it comes with the big problem. When we have multiple loss, we need to assign the weight for each loss. Like when we have more tasks, the weight is increased, and this is a key challenge because from this we need to assign each weight properly, and it's very hard to train and take time. So my research question is, how can we enhance multitask learning by adjust the loss weight automatically to achieve the optimal points of EEG classification. So from my research, I found that there are main three solutions for deal with the loss weight blending. First, it's just like we random search or grid search is coefficient manually. The second solution is we use the gradient from the network of each task to represent the learning of each task. And the last one, we use the loss slope to represent the learning behavior, like overfitting behavior or something like that. So the first work, they use the gradient from each task. And this part is like a small network that trained together with the main network to find the optimal weight. They use the gradient of each task as the input of the loss function and calculate the loss of gradient, and then they will get the weight of each task. But I try to adapt in the EEG signal, but I found a big problem that we found the gradient vanishing or gradient explosion a lot. When almost all data set that I try to apply this, it found gradient vanishing in this method. So another work that they also use the gradient from each task to represent the learning behavior of each task, and they just normalize the average of gradient and assign it to each task weight. So another way is they use the validation loss and training loss, and they just like approximate the slope of each loss, like each slope like is a gradient, like, but they use line fitting to find the gradient from the loss value, and then they just calculate the weight of each loss by the generalization and overfitting ratio. The generalization is this part. It's the gradient from the validation loss, and the overfitting is the difference between the validation loss and training loss from the current state and the previous state. So this work that I mentioned before is from the computer vision. They adjust the loss weight from the same loss function, like cost entropy 1, 2, 3. Like, but in my previous work and the other works in multimetry EEG classification, we use the different loss function from different tasks. Like it comes from different metric scale, like different scale, and they may not suitable for like multiple scale because they didn't design for it. It may it may found the suboptimal performance when use this design to my work. So my objective is I want to address limitation from the previous work and demonstrate that my algorithm can use in various types of EEG, for example, motor imagery, SSVP, and ERP. So actually, my work is like got inspiration from the previous work. I also use the gradient from each task, but instead of training the small network to find the weight, and instead of assign the weight directly, I just use the gradient and update it like similar to when we update the weight from neural network. Like it's just like gradient descent. And later I will replace this gradient magnitude from each task by normalize the gradient magnitude to prevent the gradient when it's approach to zero. This means it not will stuck in the local minima. So in the experiments, I train my multitask model with AlphaGAT with 4 different datasets. The first one is OpenVMI, the largest dataset which contains 3 tasks of EEG, and high gamma, SMR, BCI, and BCI-C2A. For the framework, I train it in subject-independent framework. That means the test subjects are from different subjects. Is either unseen subject. So in the experiment, I use the 2 multitask network that I mentioned before, MinToNet and FBMSNet, to classify motor imagery EEG data. And to compare our AlphaGAT, we compare with two others adaptive method, ADA-MT and GARAPOP, and compare to the baseline. For the results, this accuracy difference show that the dashed line is the performance of AlphaGAT is in overall is outperform the others in both model. Another comparison is I also compare MinToNet with AlphaGAT and FBMSNet with AlphaGAT with other single task classification model. The results show that in the orange and red line is the multitask learning with AlphaGAT. It shows that in all datasets and all tasks, it outperforms the others. But in a small dataset, a single task, state of the art, is perform better hours. It's because multitask learning we need more data in multitask learning. So let's look at the loss behavior of multitask learning. When using AlphaGAT, you can see that the loss rate is more smoother than the other method in both models. And the training loss and validation loss is like no sign of overfitting. it look beautiful than the others. Like other entry is look overfitting in the first training step. So to look inside in the gradient trajectory, we also simulate the multi-task choice problem to do the trajectory of the gradient. We random the 3 states. Initial state at here, like in here, and here. And so the trajectory showed that alpha grad perform better. It's not stuck in the local minima like the other. At here, it can go further and go to the global minima, while the others of 2 initial points is stuck in the local minima. Okay. That's all of my presentation. Thank you.
Any question for our speaker, Mr. Top? Mr. Top. Anyone? Maybe from, okay.
For the baseline, right?
Yes.
The baseline in this, it's like just fixed equal weight, fixed always to 1. Because it very take time to find the optimal manual weight for each. I just like assign each as one for each loss.
And another question is like you just set the hyperparameter for all condition of like, you set the number of iterations or running like it's equal in all approach.
Yeah.
Compare it.
We use the same conditions to each method.
I see. Thank you.
Any more?
So what make the alpha guard special compared to the others? Can you reintroduce this again? On the loss functions or on the... Because according to this, I can see you use standard gradients, right?
Yes.
But what it make the alpha guard special or compared to the others?
Okay. The objective is we want to find the W, the green one, right? The other is also want to find these optimal values. And the other also use the gradient, but the first one, they construct a small network to find the weight. The first one. They construct the like small network and calculate the loss and update to find the weight, right? But when applied to EEG data, it always comes with gradient explosion. I cannot train it with my model. It means that I think EEG has a low signal and noise ratio. Right? It's different from the image data that data come from 0 to 1, but in EEG it varies. Yeah. A small network with the range, different range of gradient may come to the gradient explosion or gradient diminishing problems. And the other one, they just evaluate the gradient and assign it, and they, I think it's hard to assign. When it has to assign, like it's not smooth there. My algorithm is I have a small update of weight. It make more smoother update.
Okay, so the trick that you use here is that you use a small learning rate
Yes.
to update the specific set of weights for a certain task.
Yes.
For example, task 1, you update that. But when you learn 3 tasks, do you learn the 3 tasks at the same time or one after the others?
We learn at the same time.
You learn at the same times.
Yes.
So which means that you present 3 tasks like randomly in the random manners into the network, and then the network try to learn these 3 tasks at the same time, right? Or how do you present task 1, task 2, and task 3 to the network such that you can learn?
I think because they have discussed this with Top, maybe I can help you. That the task here, maybe he haven't defined it yet. It's not the task like walking, running, or things. The task mean each part of the network. Like the first network, the task 1 mean the CNN network. The task 2 mean encoder, and the task 3 may be in another part of the network. But the whole network is just do the classification. You can show the task. I also confused at the same time when I saw this one as well. What is the definition of the task here? Yeah. Task is decoder, task is DML, task is classifier.
So this means that you have a network to do one task, but inside this network there's sub-functions
Yes.
of this network, and then you use small update rate or small learning rate to adapt those functions.
Yeah. To adapt each contribution of each
Contribution
function.
of this. Okay. But the learning rate that you use to adapt those contributions, you keep it fixed with a small number, or you change that over time?
I have experiments, but I found that a small number is good for every data set.
Okay, I see. Okay, thank you. Yes.
Any more? If there is none, so we can close. Maybe you can close the whole today. If there is none.
Okay, so is there any other questions? I think if. Oh yes, please.
Sorry, thanks for the presentation. I need to digest most of it. This normalized gradients that you showed before, so it never really settles. It keeps going on around the descents. So it won't settle, so it doesn't get stuck into local minima because it keeps going around, right? If I understood.
ในเว็บครับ
Even the slide where you had the equations with the normalized gradient, maybe. So that one, I think it never settles. It keeps running around.
Do you mean the last equation?
The
The normalization.
one at the bottom right.
Okay, the last one. Yeah, because it normalized with the other tasks.
So it never really settles. So it doesn't get stuck because it keeps going in one direction. So even when you go near the equilibrium, it still moves. And you keep moving around it, which is a good thing. I mean, it's like adding noise to get out of the
Actually,
local minimum.
the direction is in the main network. It in the same direction. Is gradient has the own direction. But the gradient that I pick to calculate, it don't have the direction. I just use the magnitudes to calculate the proportion.
Okay. I'll think more about this. I will ask you later. Thank you very much.
Thank you. So, any other comments or any other questions? Yes.
Okay, I have the question at the same way as, yes, as Professor have. Actually, it came from the last slide that show the alpha class can go to the real basin of the function without stacking. At first, I think it may be something like it can jumping out of local minima. But if I understand it correctly, it doesn't, because of it can jump out, but it not latching into the local minima. Instead, it try to like normalize the direction between different dimensions. So when we normalize the direction or the gradient, it will resolve in the true minimum. Is that correct? Or does it have another mechanism to jump out from the local minima, as Professor asked?
It jump out before because the minus sign of the gradient. Right? It means that if I have the big gradients, it will decrease the weight. That means it will jump out. I not assign. Actually, my algorithm is as when we have initial value, we have one for each weight, right? And when the gradient is big, it will decrease a little bit. That means it will jump out.
So at some point, instead of gradient descent, it becomes gradient ascent to jump out of the local minima at some condition.
Yes.
Okay, that's clear enough. Thank you.
Okay, any other questions? I think if not, then we would finish off the day and we call off the day. So thank you very much for you guys for your attentions. And I think if you have any further questions, now we are free to discuss locally now. Thank you very much.
ขอบคุณครับ Thank you so much